So that's equivalent representations. So the goal is to classify representations up to equivalence. Of course, that's going to turn out to be a hard problem for a reason that's going to become apparent in a moment, because it turns out you can keep making bigger representations with the following construction. Suppose I have two modules, G modules, V and W. You can form their direct sum. Remember, the direct sum has elements V plus W. So it's just the span of the two individual vector spaces. This comes with the group action. You can act on a vector sum by acting on them individually. You can check that this does in fact do the thing it's supposed to. That if I act with two group elements, I get this property. But since I have a group action on V, I can move the two elements in G together, and then by definition of my action, I see I do actually have this associativity type property, and it's not too hard to see that the identity acts in the appropriate way. So it is a group action. Moreover, it's also linear. So I need to take a linear combination of two vectors. In this vector space. Well, the way the group action works, by definition, G multiplies on each vector of each component separately. No, wait, that's not true. I have to be careful here. I haven't written it as separate components yet. The way this vector is defined, I could rewrite the vector as alpha v1 plus beta v2. That's the component in V. Alpha w1 plus beta w2. That's the component in W. Then I can apply the definition. Alpha v1 plus beta v2 plus G times alpha w1 plus beta w2. G is linear on V. That's alpha GV1 plus beta GV2. G is linear on W. So it's alpha GW1 plus beta GW2. So I took an arbitrary linear combination of two vectors in this direct sum. I'm acting by an arbitrary element in my group. I took this linear combination, I decompose it as a sum of a vector in V plus a vector in W, which I must be able to do. Then I use the definition of my group action here. Then I use the fact that G is linear when acting on V and G is linear when acting on W. And what did I want to get at the end of the day? I want to get alpha times G of V1 plus W1. So I need to rearrange terms. plus beta GV2 plus beta GW2. Factor out the common factor of alpha. Then apply the definition of G, the action of G. Factor out the common factor of beta. Then apply the definition of the action of G. Pull the G's out if I really have to, and voila, I got exactly what I wanted. That this is actually linear. So this is in fact a G module structure. So in other words, once I have one G module or one representation, I can keep building more and more and more. So we can't, we're going up to equivalence, there's actually infinitely many G modules. So we actually want to go the reverse direction. We want to go up to equivalence, but we only want to study the ones that can't be broken down as direct sums. So in other words, we want to decompose our representations into direct sums of smaller pieces up to equivalence. This is similar to our fundamental theorem for finite abelian groups. What did that say? That said that every finite abelian group could be written as a direct product. Of special pieces. And in that case, the special pieces were cyclic groups of prime power order. So to that end, if you can write V as being isomorphic to U direct sum W, we say V is decomposable. If not, then V is indecomposable. And the hard question is then classify the indecomposable representations of G. Well, I should say G modules, the way I've stated it. So for finite abelian groups, the corresponding question is completely solved. So I know, is it possible to do this similar problem where you're working with G modules instead of abelian groups? It's worth pointing out what this means on the matrix level. On the matrix level, if you've got a direct sum and you get a basis for the first part and a basis for the second part, then G acts on the span of the first part and the span of the second part separately. So then when you actually look at the matrices, what you're going to get is a block diagonal matrix where the first k rows correspond to one matrix, these first k vectors, and the last k or m rows, I should say, because it might be a different number, correspond to this second matrix. And everywhere else is 0, corresponding to the fact that the way this group acts, it doesn't actually send any element of E to any linear combination of the F's. And so when we talk about is V decomposable, what we're really asking is there a basis for, or is there a basis for which the matrices can be written in block, all the matrices can be written in block diagonal form. Or equivalently, is there one single matrix? What we're asking for is there one individual matrix such that for all group elements, when you multiply, conjugate by that specific matrix P you found, you end up with something block diagonal. If so, then you've now found a decomposition to your vectors, to your representation into smaller representations. Why? Because what ends up happening? Well, by definition of representation, this becomes VHP. You can insert a P inverse in the middle there, or a PP inverse. And according to our calculations, that should give you a matrix like this. It's not hard to see that that product is this matrix because it's block diagonal. On the other hand, this matrix right here has got AGH up top and BGH on bottom. And so you see, you actually have two representations sitting inside your larger representation. This isn't quite just abstract nonsense. Later we will actually look at a specific example of a representation and show how you can use these ideas to actually find irreducible representations sitting inside of it, or indecomposable representations sitting inside of it. Of course, you could ask yourself, what happens if the best you can do is to get something of this form that's, well, upper block triangular, so to speak. Well, I mean, if you multiply two matrices of this form, what's going to happen? Well, the upper diagonal is still going to just be AG times AH. That upper right corner is going to be very messy, but the lower right corner is still going to be BG times BH. So you still have a sub-representation. And so when would you have this feature happen? Or I mean, well, let's just focus on this feature. This would correspond to, well, what would you need? You would need G. Well, you would have needed to find a basis, E1 through EK, with the feature that for the last several rows, you fix some I, and then for j greater than I, G dot EJ ends up staying in the span of what's left over. That's telling you that these rows end up being here and that this stays zeros. So you're looking for some sort of thing like this. which means that if I call this thing W for G and W, once you take linear combinations for any vector in W, G dot W stays in W, right? Because W could be any linear combination of these vectors. G dot W is G times this summation Cj Ej. By linearity, that's just Cj times G Ej. And we already claimed each of these lies in W, so this linear combination has to as well. So now we're led to a submodule. It's a subspace with G dot W in W for all W in W and G and G. Sometimes this is called a subrepresentation as well. So equivalently, you'll see the word subrepresentation. That would mean phi of W is a subspace of W. For all G in the group. You use the word subrepresentation if you've already defined the representation. And you use the word submodule if you're defining the G module. So again, there's this two simultaneous terminologies going on at the same time. Notion of a G module and notion of a representation. They're both equivalent notions, so usually which term you use depends on which concept you're working with, but they are equivalent. So I often go back and forth between them. And again, the reason for that is because sometimes in applications you actually have it's easier to view it as a G module. And in other applications, it's easier to just work directly with matrices. And so the application determines which concept's easier to work with, and therefore which terminology is easier to work with. So there we have it. So this looks kind of like the idea of a subgroup. And so you could talk about a notion of simple, and here the notion of simple is called irreducible. Irreducible submodule / representation. Is a representation with no non-trivial subrepresentations, because there's always two trivial subrepresentations, namely W being the all zero vector space, or W being the full vector space. Now, an absolutely shocking fact is it turns out this problem isn't as hard as you'd think it would be. So a question or a problem would be, classify all irreducible representations. And you know how to build new representations from the irreducible pieces. So you know, a Jordan-Hilder type of program. But it's going to turn out that for certain cases, this is actually equivalent to the previous problem. So here I'll state it as Maschke's theorem. This is a fundamental result in representation theory. So it comes with one important hypothesis. Suppose the characteristic of the field does not defy the order of the group. We're working with finite groups here. And let V be a representation. Okay, a G module. And W be a submodule. Then there's another submodule. So that V is equal to U direct sum W. In other words, if your representation is reducible, then your representation is decomposable. So the corollary is that irreducible and indecomposable are the same thing. And moreover, we know how to build them up. In other words, that weird thing with the matrices I had, where I talked about, well, you know, what happens if you end up with this situation? Actually implies that there must be some other basis so that you get true block diagonal. That's what that means. So you're always guaranteed to get that, as long as you can get at least upper triangular. It's a pretty strong result. The other obvious corollary that's also called Maschke's theorem is that every representation is a direct sum of irreducible representations.